world where space and time are intertwined, one man dared to challenge the status quo. His name? Dayton Miller. His weapon of choice, a flute. But not just any flute. This instrument held the power to unleash the ether, a pervasive medium once thought to fill the universe. Miller, a physicist by trade, a musician at heart, discovered a harmonic resonance within the ether. He found that his flute, when played with precision, could manipulate this elusive medium. His melodies, a symphony of science, had the potential to shift the very fabric of reality. However, a sinister force lurked in the shadows. The Einsteinian demons. These creatures thrived in the distortion of space-time, causing chaos and disruption. The world needed a hero, and Miller was ready to answer the call.
All right, hello and welcome, lads and ladettes, to Ether Roundtable 108. Tonight, I'm going to be giving a presentation on Baloney and the radius that never was. So we'll go ahead and look at the historical narrative of Baloney, what it is that it's said that he accomplished, and how he did it. And then we're going to make some additional assertions based off of the same exact observation. All right, here we go. So who was Baloney? In the years 973 to 1050, he was a Persian polymath who traveled the lands, made many discoveries in mathematics, science, geology, geography, medicine, politics, philosophy. He was one of those, just well-rounded in
one of those.
Just one of those, just well-rounded in literally everything. Has a lot of incredible things attributed to him. But primarily, what we're going to be interested in is his astronomical feats and something he did using trigonometry. So one of the things that he did was he used Ptolemy's Geographia book and confirmed 600 locations using that coordinate system, and a book called The Determination of Coordinates Between Cities. So he basically used that coordinate system to map out a bunch of stuff in the Middle East over several different countries. So that's some of the primary stuff that he's attributed with, but he's also attributed with calculating Earth's radius using a method that was the first of its kind. So we'll get into what that means. So he's accredited with writing about 155 pieces of work, and about 120 of those are still surviving. You can find translations of the works, and some of the stuff is missing, etc., and whatever. But there is primary source material that was translated from this guy. Oh, another thing he did was he was really proficient in languages, of course. So he translated a bunch of stuff from Arabic and Greek into Sanskrit. So that's pretty cool. But anyway, you can find translations of his works, primary source stuff. So and then the identification of the coordinates using the Geographia. So he, different terrestrial features, cities, islands, peninsulas, mountains, etc., all mapped out with the geodesic coordinate system provided to us by PTOLs using the two-sphere model. Very nice. So here's what we're going to be looking at here. This is where Baloney, the peak of the mountain that he did his observation from. So here's what this looks like here. This was over in India.
So how'd he get up there?
Ooh, climbed it.
Someone just built it in the middle of nowhere, huh?
It was also a mountain
grabbed
climber.
his gear and scaled it.
Are you sure he didn't make an elevator using basic trig with in a slingshot or something?
So he actually invented the pulley, and then he pulleyed himself up. He self-pulleyed himself all the way to the top effortlessly.
No, he flew on one of the bananas, remember?
But guys, why didn't he set up at the top of the hill right behind it? Because it's way higher and you could see better up there. Why?
Oh, well, several reasons for that, Stone. He only calculated the peak of where he was going to go and climb to, I guess. So we'll cover that here in a second. But here's just some topographical features of the landscape for which he went and did his observation. Oh, I typed radius wrong in the title. Thank you. I'll correct. Thank you. All right. So if you were to be standing up on this beautiful mountain peak here, and you were looking out, and you were also inside of the Google Earth program, this is what you would see as your horizon. So as the story goes, he climbed this mountain peak, looked out with his astrolabe, measured an angle down to 6 decimal points of accuracy, did a little trig on that, and derived Earth's radius down to 1%. Sounds very impressive.
How did he tell the 100th of a degree from an astrolabe?
Ooh, so
he
had a special astrolabe built that was big enough to handle that. So the sources say.
Well, that answers everything.
He was looking at that and thought, ball.
Yeah, well, he thought ball for other reasons because he was also into astronomy, and that was sweeping across the landscape apparently. So him doing some eclipse stuff and trigonometry with latitude and longitude, mapping out the coordinates and stuff. He was super into Ptolemy's ball theory, if that's as the way that the events played out. So how did this man accomplish his goal of measuring Earth's radius, or calculating it rather? So you need three simple things. You just need an astrolabe, a suitable mountain with a flat horizon so that you can look out and measure the angle of depression, and know a little trigonometry, and also know some additional supplements to trigonometry, like the half angle approximation and other things that could have possibly occurred so that this measurement could exist down to 6 decimal places, when at the time the best they
Wait,
could have
so-
mustered was 3. And yeah, so anyway, continue.
So no one quite knows how he did it, but everyone knows that he did it. Is that what I'm getting?
Yeah, this is one of those unfortunate circumstances where there's like a translation of what he did, and then a bunch of people write things about like once they realized that the accuracy issue and stuff, they started supplementing it, like, oh, you know what else he must have done, that kind of story.
Oh, okay.
Yeah. So one of the ways that
It is
they
known.
Yeah, it is known. The Bredemisses just followed him, bro, and they counted his footsteps. And as he climbed up the mountain, it was 800,000 Persian feet, measured by Al-Biruni's actual foot. So one of the methods to get the elevation of a mountain is take two different measurements from separate distances across, and you could take the distance between the two angles there and get the elevation of the mountain peak. So that's like what they do in modern times now, but that's not actually what Al-Biruni claimed to do. Al-Biruni claimed to do the old square board method. If you guys haven't heard of the old square board method, you take your square board, you align it at an angle such that if you were to label the four corners A, B, C, and D, you would rotate the D, right, so that it intersects with the peak of your mountain there, and then you start doing trig off of that. You also, it's not listed in the three things here, but you also need a ruler to dangle off the end of D here, and then you'll need a pebble so that you can line it up to the ruler and then drop it straight on the ground, and hopefully there's no offsets to gravitational potentials not being perpendicular or anything to the geoid, and hopefully that stone just falls straight to the ground, and then once you have that, you can start doing trig off of that.
But if your astrolabe had a pendulum, you'd be all set, right?
Dude, yeah. Dude, in a gas mask.
I think if you hung a plumb bob off D, you get that all right.
Right.
You get a plumb bob hanging off D down towards H with no way into D. You stand a chance of using this method.
So that for sure, Stone. But remember, your boy didn't do that. He hung a ruler off the edge, and then to keep it straight so that the pebble would slide down following that straight line. And then when it hit the ground, they took the distance between those to get it. So maybe the pendulum would have helped.
Is that actually how they get mountain heights? Is doing this method, not this boxing, the other one?
I mean, like Stone was saying, if you had the accuracy for the base of it, I mean, you could ratio it out probably.
Like, is that what those retards actually wrote down, that they dropped a pebble and shit from D, and then they took a measurement from that where it hit the ground? Is that really what they wrote?
I mean, that's
laughable.
Dude, and maintained 1% accuracy, dude, to get the
how big was the
sub
rock?
1 degree.
Seriously, go back to that image again and look at the line where your eye has to be between B and G. Your eye has to be in the ground, looking past G at B, connecting the line to E. You know what I mean? How do you sight that?
See, I
You
was
get
thinking
under the block and put your eye, press it up against there so you're really close. And you know what I mean? Like,
yeah, it would be interesting to see some people try to reproduce the square board method, because like you were saying, I don't know how you could line that up and maintain it to the accuracy required. But going along with the story, let's just assume that this is what's canonized by this the determination of the coordinates of positions and corrections of distances between cities. So this is canonized from the translation of Al-Biruni's book, which has a different title, but this is like the translated title of what it would be. And then he describes the pebble ruler situation and all that to get the height of the mountain. So yeah,
it makes me chuckle just when you say it. Oh
yeah, I was so tickled when I read it. I was like, this is a fantastic story of it's just like Eratosthenes all over again. But so now we're going to get into the trig that he used. So now he's got the astrolabe up on the mountain. He knows how high the mountain is. He knows H, which is B right here. And from the astrolabe, he gets an angle to the horizon. And so from that, using central angle theorem, what he can do is do a little cosine function and rearrange the equation a little bit so that you're solving for R rather than using R as an input. And basically the equivalence here is the angle that's created by the dip to the horizon is also going to be proportional to the central angle here. So if you know the angle and you know A to B, you can solve for R here.
Yeah, imagine the genius of using the beauty of a flat horizon to somehow solve for globe. Watch this, guys. What a trick.
The irony.
Yeah, so there's the full series of trig functions here, and then it reduces down to just R equals H times the cosine of the angle over 1 minus the cosine of the angle there. And
okay. Also, Does anyone know how you process a cosine function without a calculator in the year 1030 or whenever this was going down?
Ooh,
so charts and slide rulers.
Yeah, so they had I got you, bro. Al Biruni was very familiar with the use of trigonometric tables. So presumably they already had it calculated out, and then they would just reference those, right?
Like a cuneiform unit circle somewhere where everyone just like knew what they were like. Okay, all right, I'll buy that.
I mean, dude, Al Biruni was the man. He measured what it came out to be 12,803,000 cubits. Which
well, then maybe that 8-step formula makes sense or whatever. Maybe it's contextually relevant. Okay.
Yeah. So keep in mind, this was measured in cubits, and then it's also within 1% of the accepted value of 25,000 miles. So, how's the cubit related to the ratio of a meter or whatever? Because what they never tell us about these stories from the past and previous units of measurement is that if you're using them for navigation and building maps and stuff, your unit of measurement is going to be a ratio of the coordinate system that you're using to determine, the distance between cities, etc. So the cubit would have had to have been related to an arc in the sky, the same way that the Chinese had a li as an arc in the sky, in the same way that a stadia would have been an arc in the sky. But they can't tell you the exact value, but they try to give like a value that's, they're like, oh, it was close to the terrestrial meridian measurement, but it's like you can only get that if it was already that, because they agree that the stadia is a ratio of the terrestrial meridian anyway. So they just the disagreement is by how much. Is it 99% or is it 87% of a terrestrial meridian? And it's like, so you can just agree to how accurate you want it to be for your story. So anyway, these units of measurement all are comporting to the current accepted value in meters, and then converted into miles. So let's see, as we go through here on the website that I borrowed a lot of this information from, there was a comment left from Walter Bislin. Shout out to Walter. Wanted to give him a special shout out,
Walter,
and thank him. So here he says, my hopeful correction error analysis tells me that to get the Earth's accuracy of 1%, you would have to measure the drop angle to an accuracy of that amount. The error due to standard refraction is k equals 0.14. In his configuration of the horizon being about 62 kilometers above sea level, that is about 8%. Did he know about refraction, or was it a coincidence to get the Earth's radius with such an accuracy? So no, they did not.
Needed yet, actually.
No, they did not know about refraction at all. So he says, anyway, an estimate of R of 10% would not be bad. In no case is the Earth measured flat. Oh, dude, thank God. It was almost, dude, it almost measured.
Before it sounded a lot like it might have been.
Before it sounded like it was just an ambiguous ratio to get the number that they wanted, but now that's plus or minus 10, like, we're good to go.
So this guy from the top of a mountain in an eyeball with a really cool, really accurate astrolabe actually detected an angle to the 100th of a degree, but didn't know about refraction swinging 8% either way on any given day, but still nailed it. Just trust us, bro. And Bislin's like, thank God for this guy. Like, I love it.
Yep. And then so here's some quick diagrams on central angle here. This one's kind of related to half gamma, which would be the drop over this distance for the thing. So we're kind of looking at the diagram that we want to use is this one right here, where the full gamma angle here is let's see, the theta plus psi here. And that gives you the full gamma amount. And then again, that's proportional to the full central angle sweep. So that's the relationship that he got there, just solving for R, having the angle and the cosine of it. So here's a quick YouTube video of a professor breaking down the story, and this is what started it all. So I saw this and I was like, oh, that's really interesting, because if you didn't assume the Earth was a sphere and you measured curve like that, that deviation, that dip, and it was just an optical phenomenon, you would derive the radius of your vision. But we'll see how they turn it into the radius of the 10th sphere here by just assuming that the Earth was a sphere to create that instead of it being an optical phenomenon. So here's a short from 3 brown, 1 blue, I think it is, or 1 brown, 3 blue. Anyway, here we go. This is Professor Tao.
There's an Arab mathematician, Al Biruni, who measured the radius of the Earth to within 1%. What he did was that he climbed a mountain with an astrolabe. He measured the horizon. The horizon was not quite horizontal. It was dipped at an angle. Here's the Earth, and here's a mountain, not to scale. Okay. So if you're standing on top of a mountain, the horizon is actually not horizontal. It's at an angle.
Right. Yeah.
Here's the radius of the Earth, and you have a right angle triangle here. You have a right angle triangle. The hypotenuse is the radius plus the height of the triangle. And if this angle is theta, then by trigonometry, this angle is also theta. And so there is an equation. I think R is equal to R plus H times cosine theta. Just from elementary trigonometry, you can relate the radius of the Earth plus the height of the mountain to this angle, and so you can compute the radius. I think it's something like H cosine. So there's a formula that you can compute the radius of the Earth from the height of your mountain and the angle of declination.
How did you know the height of the mountain?
That's a good question. I guess you could walk around a bit and take angles, and that part I don't actually know. With enough trigonometry, you can do it.
This comes from an interview with Terrence Tao about all of the...
Dude, with enough trig,
anything is,
you
you can do it.
dude, you can do. I just did it. Look, you can do it.
Like if
You
you
know,
had
the way
to,
he explained it, I would almost believe it to be 100%. He was so confident. It was so like down to earth. It made sense quickly to my brain. If I don't think about it, I'm like, yeah, that dude totally figured out Earth's radius with a pebble and an astrolabe. Wait a second.
well, if you had to choose between they just walked around and took angles versus how it was actually described that it was done, which one would you do?
Well, go back to that other image just for a sec. That one. That equation is only true if point 1 and point 2 are at the same altitude.
You mean
what the flat line means.
the elevation of
Yep.
I got you. Oh.
Mhm.
Oh. Dude. Stone for real? That's
Wait,
hilarious.
For real, dude. That is
That's-
only true. This
Dude,
equation is only true if elevation point 1 and elevation point 2 are the same.
You know how they claim to measure like mountains in India and stuff, right? They basically say they walked around at different distances. So dude, that's
And
hilarious.
they know exactly what their altitude is for sure, dude.
Oh no,
Um,
dude.
But I'm almost positive you can't use triangles on Globe Earth because that's where those Czech lads spent 2.5 hours telling us over and over again, and that there's no
Oh.
possible way to use triangles for Globe Earth, and by doing so, this whole thing is invalid by Czech argue logic or whatever.
Oh no, dude, that's amazing. It's only valid if they're all in the same elevation. GG. Yeah, dude, they would go miles.
like
They
that?
would go multiple miles apart to get it because you need the further and more
For
data
sure.
points. Dude, that is
For sure.
fantastic, Stone. You're the man. That's hilarious.
Oh,
So-
Stoney,
so-
excellent.
So Stone, this is the globe method where you drop the pebble, so you don't have to have equal elevations across
I'm
the
digging that
distance.
one.
It's yeah.
I
This is the
pity
one
the
we're
guy
doing.
who had to stick his eye underneath the block next to point C there and look up past B to E. He's like, okay, I'm insured. All right, my family will be okay if I take this.
That's hilarious. All right. So in modern times, there's been some reviews of Alberuni's work. And what I was talking about earlier with the accuracy required to actually derive Earth's radius, you need to get an angle down to 6 degrees of accuracy to get the exact value of 1% of the current accepted value. So we're here looking at the decimal placage here that's required. And now this guy was saying, oops, I didn't cite that one. Well, in this paper, this guy was saying that if Alberuni was aware of the half angle approximation, what you can do starting from 45 degrees and just dividing down, you could eventually get down to the 6 decimal placage here for 0.703125. And that's the number that was required to get them to 6,368 kilometers.
Nothing for one of those guys.
and-
one of those guys
and-
can do anything.
And keep in mind, no refraction correction, 8%, which gives an 8% error, and then they needed 1% for the measurement to even give the possibility of deriving something that's 1% of the accepted value. And then on top of that, there's the issue of contrast reduction, which was pointed out in a previous presentation that I went through regarding the terminology of incoherent photon scattering, which is essentially the reverse of refraction. So if refraction coherently scatters photons such that it preserves the image and lifts it up, etc., incoherent would be the loss of information. And what that looks like is, when you're looking out at distant mountain peaks that are distant from one another, you'll notice that one of the peaks is brighter than the other one, and then the one that's further away looks like it's got a dim layer over it. So that's what and what the cause of that is that the air in between you and the mountain is causing the scattering of light, and that light isn't reaching your eye, so it's not as bright for you. So they call that contrast reduction. So mechanistically, the idea that he climbed to a mountain, and real quick, in the paper that we went over for that presentation, they were saying that if you're 2 kilometers above sea level, it's impossible due to contrast reduction to determine accurately where the sky intersects with the ground geometrically, because all you're going to see is like a white line blur between the sky and the earth. You're not going to have a definitive geometric intersection point. So this guy going 62 kilometers up, not accounting for any refraction or contrast reduction or anything like that, just centers his astrolabe right in the center of that geometric intersection where you can't even see it because it's just a white line. But he got it down to 6 degrees of 6 decimal places of accuracy.
Nailed it by
All this
accident, as
lands-
Bislin said.
All this lands squarely in the lap of those who worship at the altar of the golden theodolite.
Yeah.
Hey, Alan.
What's up?
So we know the exact answer he got, but this is saying we don't know his inputs or the equation he used to solve it.
Yeah, I think we're speculating. I think we said that. Like at the beginning, it's like, so here's the story. Nobody knows how he did it, but everyone knows that he did it. And so
But they know the exact number he got for the answer. That doesn't make sense.
Yeah.
Yep, that's how we started.
He had a pocket full of rocks, so we know that.
Yeah, there were pebbles and a ruler involved.
And now I think they've over time they put forth the most scientifically based reasoning as to how he could have done it. I think that's where we're at. That's what we got right here.
But yeah, essentially. So the big takeaway from this is that cubits slash the mil is an unknown length, but there's a scholarly gentleman's agreement that whenever they're discussing it, they're always discussing it in terms of the units being a ratio of a terrestrial meridian, but they just disagree on how much of a terrestrial meridian it was. Same thing for the stadia, just requires a scholarly gentleman's agreement on the ratio of a terrestrial meridian. And then the li, which the Chinese used and defined as an arc in the sky for their mapping and units of measurement and whatnot. So what they say now is that because the Chinese were actually using the same celestial sphere that is used now, they say that the li is half of a meter. So anything calculated by the Chinese back then is automatically half off. It's just they're half wrong no matter what. So everyone got together and agreed that the Chinese are that the Chinese that circumnavigated the South in before anyone else did it, they did it by being half wrong about the whole thing. Just insane. It's like because the importance of this, of making it half wrong, is like they don't want you to know that you using a unit of measurement that's a part of the coordinate system that you're using is always going to be internally consistent. So defining the Earth in terms of its 25,000 miles of circumference or what have you, all of that is just predicated on trying to make that a physical, meaningful thing that exists as like an external measurement that confirms the shape of the Earth. That's why they went through the trouble. Well, it's partially why they went through the trouble of redefining the length of a meter in the 80s to being equivalent to a certain wavelength of light at a certain temperature, and then also defining a second as an oscillation of a cesium atom. So, like, relating those two makes it seem like it's we've independently verified it now, but the speed of light over 1 second in inches, you can ratio that into meters, and it comes out to be the exact same thing. So it's never not been anything different than a ratio of an arc in the sky, and it's just, you just can't let people realize that. So a meter currently defined as 1/10 millionth of a terrestrial meridian, and that's section of the coordinate system itself, 1/10 millionth of it. So when you use said coordinate system to computate distances between places, like our buddy Baloney did in his book, where he confirms the location of 600 terrestrial features and locations, it's not going to be wrong. It's going to be a ratio of the coordinate system. So that's the big takeaway from this.
Nice.
All right, that's all I got for old Albaroons here and the story of the radius that never was. But yeah, so if you don't assume that the Earth is a sphere, and you just took the measurement as is, because they could probably do something like this now with a regular theodolite and trig it out and find the globe all day. But if you don't assume it's a globe, you're just measuring the same exact radius that is used for celestial navigation, which we say is the radius of your field of vision. And then that same exact radius, or not same exact, but close to that radius, was derived from Brian using the eclipse data of the shadow length and the angles of the observers along the whole length of the shadow, all deriving the same altitude, which gives us a altitude of the celestial sphere, which also gives us a radius, which comes out to be the same thing that these guys are calculating out with their square boards and astrolabes. So in my opinion, I think this is just a measurement of visual space that's been misinterpreted as the radius of Earth rather than the radius of your vision. Any
Didn't
thoughts?
Gauss do something similar?
Yeah, so let me quote from the historical archives here. Gauss measured the difference in elevation between mountain peaks and found that they were not different from zero. Like the difference in elevation.
Elevation, yes.
Yeah.
Okay.
So, in other words, he measured no drop over distance, but somehow also
Calculated the globe right out of that, dude. That's a really good trick that they can do, right? Like, hey, see how flat this is? Watch me take this measure of flatness, and I'm gonna round to the globe. You see this formula? Well, if I invent a radius and I force it, and then I just change these terms around, boom, globes. Did you guys see that? It's crazy, dude. They're really good at it.
It's a very common trick they use.
It's still mystifying to me. I'm still impressed. Yeah, nice. I never heard about this other method of measuring the. Like I said, I've only ever heard of the sun method, where as a glober, where you definitely know the shape of the Earth is by when you stare directly into the sun, and then you just take sun angle measurements and shadows, and you do some math based on an assumption, and then you can get the circumference quite easily, which can then use to get the radius. I had only peripherally heard of this story, and I kind of think I laughed at it, and I never really knew about it. But now we have ammo to, of course, address directly this claim of Earth radius measurement. So thank you, Alan.
Yeah, one of my favorite breakdowns was when you were going over the Eratosthenes one, and it's entirely dependent on knowing the exact distance between Syene and Alexandria, and then the only way that you could make that be the accepted value now is by making it is by making the stadia a ratio of the terrestrial meridian, and then just like being mystified that it all worked out to be exactly what they say it is now, using a different unit of measurement that's also a ratio of the terrestrial meridian. So
Yeah,
like when you
magic.
like when you see that level of the trick, it's just, it's like, oh, so you could definitely measure that, but it's like the assumptions baked into it and the output of it, like, is that physically meaningful, you know? Because we could definitely calculate some stuff, but is it physically meaningful is the question.
Yeah.
Or where
You know what
does
it
it
is?
apply, rather? What's up?
Being able to identify the internally consistent system with which you're operating. Like, because you need, without an external reference, it becomes hard. Same thing with surface measurements. Like, how do you prove Earth curvature? You need an external reference. That's why we turn to the stars. So I think that you just accept like the internal model that you start with. And I think it's hard for anyone to kind of think outside of that.
Yeah, it's keeping it compartmentalized and making it seem like it's a independent system that just so happens to also measure the Earth is how they get away with it.
Like, oh, didn't you know that whenever you mention lat long, that's the globe? Matter of fact, if you ever take the longitude and latitude of any two positions and then use that to compute distance, that's also the globe. You didn't know that? Well, no. By definition, those two things are tied specifically to the coordinate system with which you're calculating. Right? Those 2 points have to be represented as latitude and longitude, which is the coordinate system of the sky. So it seems silly for them to be like, duh, it only works on the globe. Well, no. It only works in the spherical coordinate system from whence it came.
From whence it came. Well said. All right, if there are no other thoughts or comments, we can wrap up for the night. I see D3 with an unmuted mic.
Dangerous.
So is my understanding correct here? We know he built an astrolabe, and he had to get an angle measurement accurate to 6 degrees in order to get his accuracy, but we don't actually have any record of what he recorded for that angle.
Yeah, so what he recorded for the angle is right here. So his actual angle here that is purported from, what he says is 0.34 of a degree.
But that's not 6 digits.
Yeah. So, like dude was saying, the only way to get that out would be to do like the half angle approximation thing to get it out that way. So like the story just like completely falls apart.
Yeah.
But it's like still supplemented and told through the angle of 0.5, and then this dude did all his math based on dividing that out to get it out to 6 decimal places.
If you just showed the math screen, like in a high school class, if you just showed that one screen that has the formula, and you told me the story that the Asian dude told you on the YouTube, I would buy it. All right, like go back to your math slide. Like no. Like if you just played me the video and then showed me that one slide, I think I would buy it. Like, oh, some dude from ancient times figured this out on a tablet with some rocks and dropped it from. Yeah, no, totally looks good, Chief. Like look how convincing it is. Yeah, you're like, oh, wouldn't you know it? This is a formula that we use today to determine sphericity all over the globe. You're like, no way, dude, use the same formula.
Yeah, but we're not allowed to use this formula because this formula means globe, I guess, or something. Like it's always going to be globe. Like this actually only calculates globe, if you didn't know.
I feel like it uses the radius like 9 times.
If you knew the radius, you could, yeah.
And they figure this all out without even knowing about refraction at the time.
Yeah.
Dude, nailed it. Like just pocket shot, like from the hip, nailed it within 8%.
And then within 8%. And then magically, we all learned about refraction. It turned out to be the exact same freaking thing. Man, this guy have a statue. He should have.
Yeah, that's how we know what he looks like, bro. Just like Eratosthenes and Plato and all them people, we know exactly what they look like because of their statue.
Getting all the variables all wrong and everything like that, but nailing it, and it pans out. 2,500 years. I love this guy. This guy's awesome.
Al Baruni, as they say. Old Al Baroons. All right, well, we're going to wrap up for the night, lads. We will be back on... What are we doing this week? I think we're going to do something on Thursday as well. Just don't know what yet. And then Friday will be Twitter Community Night, hosted by Brian Sweet. So follow him on Twitter for Friday Community Twitter Night. And then what are we doing Sunday? Sunday for Globebusters, we're going to have a guest presentation from our very own Vambi. He's going to be presenting on refraction and boundary conditions to create the lifting of images, etc. So that'll be awesome.
That sounds full on.
Nice.
Awesome roundtable, y'all.
Thank you, Mr. President.
Nice.
I thought I heard JT. What's up?
Yeah, I tend to listen from YouTube because of the frequency in which I must pause because of family. And um, man, it was so cool. Just like what you guys were talking about, the angles in the box and eyeballing it up this way and dropping a rock. It's like little did they know they're still trying to measure how we see the world, and the globe was invented by how we see. So they're not dialing anything in with their box. But I talked to Plain Reality, and it surprised me. He said he's going to do like work with a guy to do an actual scientific paper on perspective, and that's really awesome.
Outstanding.
It's awesome. And real quick before we close out, someone asked in the comments about Alberuni and what he did regarding map projections. So he was the first person to make a Mercator projection, and then that technology was lost and then rediscovered by Mercator later.
I didn't know that.
Yeah, he was super.
That makes total sense.
He was super into stereographic projections and all of that. And then, like I said, that technology was lost, and then it was rediscovered by Mercator.
See you later, Mercator.
All right. Well, see you guys.